Okay, we're going to go through B plus trees, B trees, and external data structure. So everything around the B plus trees topic. We're just going to go through everything. If there's any questions throughout, drop them in the chat. Otherwise, I'll just steamroll through the slides. Okay, so we're going to start with the definition of a B tree. A B tree of order M is a type of n-ary tree with some particularly nice properties. So every node has at most m children. Every non-leaf node except the root has at least m over 2 children. So m is the order of this tree. The root node, if it's not a leaf node, has at least 2 children. And a non-leaf node with C children contains C-1 search key values, which act as separators or discriminators to guide searches down appropriate subtrees. We'll look at what that looks like graphically as well. All leaf nodes appear in the same level, so a B tree is always balanced in terms of the nodes and the level of those nodes. B trees are always height balanced, yep. And update and search, as a result of that, is logarithmic in all cases. It's never going to be like a linear, it's never going to be like a linked list because all of the nodes are obviously height balanced, so it's like a perfectly balanced tree. And so a variant of the B tree is called a B plus tree, and this is what most databases use, and it's a common external data structure in use. In terms of external data structures, all that means is something that's stored on secondary storage. It's not stored in memory. So the data structure can persist beyond the program execution. It can grow to sizes larger than memory, and we can access and update it by multiple different programs at the same time. So B plus trees, we'll go on to the definition of them, but the idea is with secondary storage, we store things in blocks. So we pull blocks from memory, or we post blocks to memory. And so we can only edit a block at a time. So if we want to edit one bit, we have to pull out the whole block, edit the bit in that block in memory, and then kind of upload it, kind of store it back into the hard disk. So it's really inefficient if we only want to change a small amount of data. In spinning hard disks, the time to read or write a block includes time to move the disk head to the correct track, time to wait for the block to spin around to the disk head, time for the disk to spin until the whole block's passed, and then so it's mainly these 3 steps, and reading or writing consecutive blocks is a lot faster than scattered blocks around a disk, and that's why you have things like disk defrag. But the main takeaway from this slide is secondary storage. We can only edit blocks at a time, and it takes a lot longer than just normal CPU operations to read and write between storage on external data structures or in external data devices. Okay, B plus trees. So there's a few terms we use in B plus trees. Data record, this just refers to some entity object or some element of data that needs to be managed by the B plus tree. So a student record might have an ID, a name, an email address, a student ID, just a bunch of information about them. Key value is the value by which we identify the record. So if you imagine in a database, this might be something like the primary key. But we can have multiple key values, even if they're all not the same in a B plus tree. Discriminator is the value we use to decide which path to take down. So in our nodes, those are the values that we use to decide whether they're going to go left or right. And usually this is the same key value. This is almost always the key value of some record, but in principle, the discriminators don't have to be the key value of records. They could be anything. And then we have disk addresses. Disk addresses are the offset from the start of some disk file to a particular block in the file. So every file is stored on some external data device, and the disk address tells us where in that file, almost like an index in that file, where in that file a particular block is containing something relevant to us. And so we execute this seek operation with our OS, and this can read that block from the file or write that block to a file. So you can think of a disk address as just a memory pointer, but instead of it pointing to memory, it's pointing to something on the hard disk. Okay. So B plus trees, their nodes are designed to fit in disk blocks so that reading or writing a node corresponds to reading or writing a single disk block. So we pull out nodes, and that node is essentially one block in a hard disk. Most description of B plus trees will start with the order of a B plus tree, but really, B plus tree implementations usually just look at how much stuff we can pack into a block. So you might not have the same number of children for every node. Every internal node, it might differ depending on how big or how small the different records are that you're trying to store. Yeah, so that's just something to keep in mind. And note that since keys can be of variable length, the maximum number of children is not a fixed number. So some nodes might have more children than another. That just depends on how we implement the B plus tree. But the idea of how we can search, insert, all of that comes down to logarithmic time complexity at the end of the day. So there's two variants of B plus trees in common, which we can call record embedded and index B plus trees. You might not see these terms around on other websites. This is one that sort of was created. These aren't like official terms, but a record embedded B plus tree stores the data records in the leaf nodes of the B plus tree. So this is good when you want to just find records by one search key, like a student ID, but you don't want to find it by another search key, like student name, for example. And this is also good if you just want the B plus tree to manage all of the data. So if you delete the B plus tree in a record embedded B plus tree, if you delete that tree, you lose the data because the data is inside the B plus tree. Yeah, so that's record embedded B plus trees. We also have index B plus trees. So index B plus trees store only key value pairs and disk addresses in the leaf nodes, which identifies the disk block in the separate file of data records where the record with the corresponding key values reside. So imagine our leaf nodes. In a record embedded, all of them are the actual data records in the leaf nodes, whereas in an index B plus tree, we might have a student ID, for example 1, and then some sort of disk address which tells you where to find information about student with ID 1 in some other file. So this is ideal if the data records are kept in blocks separate from B plus trees. So if we drop the B plus tree, we don't actually lose those data records because the data records are in a different file. Multiple B plus tree indexes can be created on a collection of data records. So if we have a data file with a bunch of student ID records, we might have one index B plus tree indexing based on ID, one indexing based on name, and so we can sort by multiple attributes. And this is good for things like databases because we might want to select the top 5 based on student ID, based on grades, based on some other attribute. So we're not limited to only using one specific key like a record embedded B plus tree is. Okay, so let's dive deeper into record embedded B plus trees. It looks something like this. So we have a root node here, and we have some leaf nodes. In this case, this is of order 4. So, wait, I believe it's the order's the number of children. So, every node has at most m children. So, this B plus tree down here is of order 4 because every node has at most 4 children. So we have a disk address, and this disk address is everything that's less than 13. And this disk address here points to a leaf node, which is everything that's greater than or equal to 13 or less than 17. This is greater than or equal to 17 and less than 24, and then greater than or equal to 24. So hopefully those pointers make sense and why these values in the nodes are significant. So these values here, these key values, are our discriminators, and these disk addresses just point to some other block or some other node in our B plus tree. Okay, so what these stars mean, these green squares with these stars after, that just means that we're storing some records in those leaf nodes. So we're storing 2, and we're storing all of the information about 2, the record associated with the key value 2. Here we're not storing the records in the non-leaf nodes because these are just discriminators which we use to decide which path to take down to find a record in the leaf node. So the only place you'll find those records is in the leaf levels. And note that not every single key value has to be in the non-leaf nodes. As long as we just have them all in the leaf nodes, we only have 3 different discriminators here. But we can still access all of these different nodes by using them to decide which path to take down. So after we insert some record 4, we have to do a few operations. So say we want to insert this 4 here. Let's write this out and see exactly how that works. Okay, yeah, let's have a go at inserting the record 4. So we want to insert 4. 4 is going to be less than 13. And we reach this leaf level. So we want to insert 4 into this leaf level. So we want to kind of pack it here in between this 3 and this 5. But we can see that we can't actually do that because there's not space. We can only fit 3 values or 3 records in this block. So what we're going to have to do is we're going to have to split this up into 2 blocks. So we'll have 2 and 3 in one block. And then we're going to have 4 and 5 in another block. So it's going to look something like this. Okay, and then these we're going to update the next in prev pointers so that this is still that doubly linked list. Yeah, okay, cool. So now we've created 2 nodes. We've added the 4 here and we've split that up into 2 nodes. And then what we want to do is we want to update these pointers. So yeah, if we wanted to insert 4, obviously we'd insert it into that first one, this first block, but we'd have to put it here. So we'd have 2, 3, 4, and 5, which are trying to squish into one block of 3. We can't do that, so we split this into 2 blocks. So it becomes 2, 3 in one block, and then 4, 5 in another block. So yeah, we'd split this into these 2 nodes. We'd update these pointers. I should also write these in. But yeah, we'd update these pointers. This would then point to this, and this wouldn't point to anything. We get rid of this node here, and now we want to copy this 4 into here so that we can have something like this, where this 4 is pointing to, where this 4 is pointing here and this is pointing here. But we can't do that because we can only store 3 things in here. So we have to apply this post operation again here. So now we have 4, 13, 17, and 24. We can't fit those in 3, so we split it down the middle. 4 and 13 go in the left, 17 and 24 go in the right. So we have something like this. Let's 17, 24, this would stay as it was, but now we have 4 and 13 going in this node here. And so what this means is this pointer can point here. Everything greater than 4 is this, and everything greater than 13 we can put here. And then I believe we can just point this 17 one straight here. Let's just check that. Oh, one more thing. Now that we've reached this point, we can't actually... This isn't quite valid because not everything's under one root node. So now what we'd do is we'd have, greater than or equal to is to the right. But now we'd need to also make a root node. So our root node would be something like this, where we have 3 nodes. Again, these will have their locations. But we'd take the first value in this second node, so this 17, because it's greater than or equal to, this preserves that ordering. So anything greater than or equal to 17 is here. Anything less than 17 is here. But we don't actually need this anymore. Because this isn't actually storing any data, we can just get rid of this, and we can essentially shift that 17 up. So this just becomes this. Does that kind of make sense? So now we've moved the 17 up here. Everything less than it is on this side of the tree. Everything more than it is on this side of the tree. So we pick the lowest record. So we pick the lowest record in this right, and we post it up. If it's actually got an asterisk, which means it's storing some data, we can't get rid of it here. But because the 17 here didn't have an asterisk, this was just purely a discriminator value. We could just move it up. Cool. But yeah, that's how we'd go about adding this 4, inserting this 4 into the tree. And I believe we got the same result here. So we had the 17 at the top. Initially this would have been 17, 24. We moved the 17 up to make a single root node. Both of these are the children of that root node. And then we have our leaf level nodes down here. Right, let's move on. Okay. So that's how we can insert. Search operations, we start at the root and we just follow the path down, the discriminator values. So searching and also searching for records in a range is quite nice. So if we want to search for a value in this tree up here, for example, say we want to search for 15. We look in this root node, 15 is going to be in this disk address here. Follow this down, and then we just search through this. Is 15 in here? No, it isn't, so 15 is not in the B plus tree. If we want to search for records in a range, so for example, from 4 up to 20, or let's say 4 to 24, we'd look at where 4 is, so the lower bound. That's less than 13, so we'd go down here. Linear search through this. 2 is less than 4, so we don't care about that. We don't care about 3. We go up to 5. 5 is more than 4, so this is going to be our first value in the range. 5 with the record. And then we just follow these next pointers up. So then we see 14. 14 is in our range. 16 is in our range. Follow the pointer up to the next leaf node. 19 is in our range. 22 is in our range. Follow the pointer up to the next leaf node. 24 is in our range. 29 is not in our range, so we stop there. And we found all of the records in the range of 4 to 24, and that's just these So that's searching for values and searching for values in a range. Inserting, so when we want to insert, we've seen how we can insert. We search with the key of the record to find where we need to insert it. If there's space there, we just insert the record, and that's fine. But if there's not space there, like the example we looked at, then we want to have approximately half the records in the left and half in the right in 2 new leaf nodes. And then we want to post the value of the lowest record in the right page as a discriminator to the level above. And then we recursively do this post until there's a gap, or we have to make a new root node. And we'll only increase the height of the tree if we make a new root node. If we do a bunch of splits and stuff, but we don't actually make a new root node, the height of the tree will stay the same. Cool. Okay. With insert, yeah, so the tree only grows in height when the root node splits. Hence, every path on the root to any leaf is the same height at all times, so the tree is height balanced. No node is ever less than approximately half full, except for the root node. So none of the other nodes will end up being less than half full. Deletion works as the inverse of insertion. Whenever a record's removed from a leaf node, if the node becomes less than half full, then the records of it and its neighbouring nodes is distributed between them. If the nodes become less than half full, then the nodes are merged and an entry removed from the level above. This can cascade up until the 2 children of the root are merged and there's just a new root node instead of 2 smaller nodes. Yeah. Okay, so yeah, that's insertions, and deletions is pretty much the same but opposite, which we could probably find some examples for after. Bulk loading. So creating a new B plus tree index on a set of records can be done by iterating over all the records and inserting them one by one into the B plus tree. But this is inefficient because we're going to have to keep searching down the B plus tree every single time we want to insert another record. So bulk loading is a more efficient way of inserting or constructing a B plus tree from a set of records. And so it comes in these 3 steps. We sort the records in some sort of ordering system, which we're going to use to decide just some sort of sorting convention. Usually it will be in ascending or descending order. And we insert them into a leaf level set of records, connecting those leaf blocks as we go. And as we construct those leaf blocks, we construct a parent node by inserting leaf disk addresses and discriminators into that parent node. When a parent node becomes full, split it as usual for insert. So this results in all of these splits happening along the rightmost path in the tree, rather than being randomly distributed around the tree across many different paths. So this is more memory efficient because we only have to keep the nodes on that rightmost path in memory, and everything else can just be stored externally. So this is much faster, much greater performance. Let's just look through an example of that. So let's say we had these 8 numbers, and we want to perform bulk loading to generate or to construct a new B plus tree. So first thing we do is we sort it. So after sorting, we should get a list 2, 4, 5, 6, 7, 12, 22, 43. Let me know if I have done that a bit wrong, but that looks right to me. Okay, so this is our sorted list. And now, one by one, we insert them into leaf nodes. So let's say we have a tree of order 3 for simplicity. Okay, so we insert 2, or let's just draw out what a leaf node will look like. So our leaf nodes will be something like this, where we have 3 values in them. These are representing records, by the way. We assume we want to insert the records into the B plus tree leaf nodes. So this is one leaf node. I'm just going to put it here so I can copy paste it. Okay, so we create our first leaf node. 2, 4, 5. Okay, cool. So we've got our first leaf node. And this is just the root node of our B plus tree, so we don't actually need to make anything up here yet. But as soon as we try and insert the 6, it won't fit in this leaf node, so we need to create another leaf node. And we're going to put the 6 here, so we can update the next and prev pointers of these 2. We're using m equals 3, so, sorry, m equals 4 it would be. Yeah, so we can store 3 discriminators in every node, and every node points to 4 children. So we've inserted these 3. As soon as we go to insert that 6, so let's just take these off. As soon as we go to insert that 6, we have to create another leaf node, and now we don't have a single root, so we have to make another root node, or we have to make another node, and this is going to be a root node of our tree. So this is going to look like this, and we're going to, these would all actually be records, so it'd be a good idea to put stars here. And we want to post this 6 upwards. So we can move that 6 here. So everything less than 6 is now in this node. Everything greater than or equal to 6 is in this node. Okay, so we've inserted the 6. Then we insert the 7. We can do that fine. That's not going to create any more nodes. We can insert the 12. That's fine. 22. When we want to insert the 22, we're going to have to make another leaf node and insert it there. Update these pointers, and we need to point to this leaf node. So we'd have this 22 being posted up into this node, and this pointer going to here. And then we just insert 43. But yeah, that's how you'd sort of bulk load elements into a tree. And if we made more and more nodes, we might need to make another node here, and then we might need to split this into 2 nodes, something like this, and then post this up here, so then we'd have something like this. But the idea is we keep extending on this rightmost path. We'll never touch any of these nodes once they're full. We're just going to keep extending on the right, and then keep extending on the right, and the right, and so on and so on. So we only need to keep these in memory. We don't actually need to keep any of these in memory. So index B plus trees, right? So there's 2 subvariants of the index B plus tree. So we looked at record embedded, where the records are actually stored in the leaf nodes. With index B plus trees, there's 2 types we look at. So we look at primary index B plus trees. I'll explain this one first, because this one's probably easier to wrap our head around. So here, in a primary index B plus tree, the records are kept sorted by the key value used in the B plus tree in the data file containing the blocks of records. So the leaf nodes of this B plus tree only store some discriminator values, and they look a lot like the internal B plus tree nodes, but they also have forward and backward pointers. So they just store some key value or some discriminator, which just references some sort of data in the file. So in primary index B plus trees, we assume that the file is sorted. We'll look at what that looks like in a second. But on the other hand, with the secondary index B plus tree, the records may not be sorted in the data file. So every entry in the leaf nodes of the tree contains a pair of the key value and a disk address, which identifies where in the block, where in the file to find the information about the record with the corresponding key. Leaf nodes also have forward and reverse pointers, just like primary index B plus trees, record embedded B plus trees. But let's look at an example of a primary index B plus tree. So something like this. Let me just screenshot this so I can annotate it. Okay. So something like this. We have our root node. Note that we also have these 2 disk addresses on the side. So the idea is this disk address is supposed to be a prev, this is supposed to be a next, but they don't actually point to any other nodes in this case because we've only got 1 level. And then we have these disk addresses here. So what this tells us is anything that's less than 13 is going to be here. Anything that's between 13 and 17, inclusive of the 13, is going to be here. Anything that's between 17 and 24, inclusive of that 17, is going to be here. And then 24 or more is going to be in here. So it's quite similar to the B plus trees we've seen. Again, this is like a doubly linked list. But the thing to note here is this is our leaf level. This is not our leaf nodes. This is our record file. And so this is the bottom node in the actual tree itself. And these are pointing to the actual record file. So this is a primary index B plus tree. After inserting 4, for example, I believe this is the same tree as before. So we'd insert the 4 there. We'd split this up into 2 leaf nodes, or 2 nodes in the record file now. So we'd have 2 and 3 in one of these blocks, and 4 and 5 in one of these blocks. And then in the leaf level of our primary index B plus tree, we'd post this 4 upwards into that leaf node. And if we tried to post this 4 upwards, we'd have to split this node in 2. So it'd be 4, 13, 17, 24, which we can see here. We made 4, 13, 17, 24. But we need a new root node, so we post this 17 upwards to make a new root node. Everything less than 17 is then on this side of the tree. Everything greater than or equal to 17 is on this side of the tree. So it essentially adds another layer we can go across. Our record file, note, is all stored in order. So 2, then 3, then 4, then 5. So our primary key is the sorting key used to sort the record file. Oh, what just happened? So that's primary index B plus trees, and note the record file is sorted. It's sequential. Secondary index B plus trees. So yeah, we said our definition of secondary index B plus trees is the records may not be sorted, and we can see this down here. In our record file 17, 24, 4, 13, our record file is not sorted. So every value in the record file has an individual entry in the leaf level. So we have to reference every single record in this leaf level, unlike our primary index B plus trees where we don't. So these aren't just ranges anymore. So for example, this disk address here, let me also copy this. So this disk address here, for example, does not point to records between 4 and 13 now. This points to the record 4. So you can imagine it as this first, so in the leaf level, this very first and this very last are used for the prev and the next disk addresses. And then every record comes as a discriminator and an address. So we have this 4 and this address. And then we have this 13 and this address. And then we have no value here and the address. And we have the same for this 17, 24, whatever, whatnot. So what this is basically saying is our value here. So to find the value 4, we follow this disk address, and this will take us to the block containing the record 4. And to find the value 13, we follow this disk address to take us to the block which will contain the record 13. So every single record file here has a corresponding discriminator in the leaf level, in some node somewhere in the leaf level. And so the root node doesn't need that, obviously, because we just want to use this as a discriminator to decide whether we go left or right. But yeah, everything in the leaf level will always have a value or discriminator for every single record in the record file, depending on whatever key we're using. So you can note that every value in the record file has an individual entry. Hence, we see key values in the leaf level that may occur higher in the tree. So this 17, when we post it upwards, we can't get rid of it in this case, because with a secondary indexed B plus tree, we have to keep it here so that we have some reference to that 17. So that's why it's repeated here and here, whereas in another type of tree, you might see just the 17 here, and because this isn't an asterisk, you could probably assume you get rid of it, but you cannot do that here. You have to keep it there in the leaf level. Cool. Does that make sense to everyone? Are there any questions? So let's look at complexities for B plus trees and all the operations we can do on them. So the B plus tree is an n-ary tree, which is height balanced. So search is going to be O of log n. In practice, search will take O of log base m of n reads, where the fan-out ratio of the tree is m. The fan-out ratio is just the number of children in each node. And so with something like a 4 kilobyte block, a 4 byte integer key, and a 4 byte disk address size, with every block being half full and even assuming a little space in each block is taken with extra administrative information, this gives a fan-out ratio of at least 250. I believe the mistake here was, I think Alan made a mistake here. This should be tree of height 0 is 250 records. If we have a tree of height 1, then that can fan out into 62,500 records. Tree of height 3. Well, the idea is you don't want to really look at the exact values here. Obviously, some of these will take up discriminators, memory addresses, all of that. But the idea is it multiplies really fast, and it's an exponential growth. So for every height we add, we're sort of raising it to another power. And so that's why searching is the inverse of that. Searching is logarithmic, and with the base of whatever the fan-out ratio is. So, yeah. This is quite an underestimate, because on average, nodes will have more entries in them, and the block size will usually be larger than 4 kilobytes. But yeah, again, this is just an example to show how B plus trees, we can store so much more data, and we can do stuff in 4 disk reads, for example. We can search a collection of approximately 4 trillion records. That's 4 billion, right? 4 billion records in 4 disk reads. So it means we can store so much information, and we can access exactly what we want without going through all of that information. Note that the cost of the disk read and disk writes are so much larger than the cost of memory processing. And so we can ignore those memory processing costs, and we just care about the disk reads when we're looking at complexity of this sort of stuff. Oh, okay. So, yeah, with a B plus tree complexity, note that, yeah, so because the disk reads and the disk operations are so much larger than the cost of memory operations, we just consider the disk operations. We don't really care about the memory operations. They're negligible when we're calculating the time complexity of these operations. Insertion has the same order of complexity as search because we're just doing a logarithmic, we're basically searching and then inserting, and both of those operations are logarithmic. So overall insertion is just logarithmic. That's everything on B plus trees.